Assalamu alaikum. Hi everyone. In this video, I would like to introduce the basic idea of programmable logic devices, or more popularly known as the PLDs. By the way, before we go into detail regarding the PLD, let us begin with the basic concept of the combinational logics. Suppose that we are assigned to realize a logic relation between an output with multiple inputs. In real applications, the digital inputs can be the signal from digital sensors like the temperature sensor, pressure sensor, water level sensor, and so on. And the output can be the signals to trigger an alarm, to lights up an LED, or the signal to move an actuator. Alright, in this example, let's say the problem is to realize an output Y, let's call it Y, subjects to inputs, let's say A, B, C. So we can write Y is the function Y is the function of A, B, and C. Let's say the situation of the conditions of the system is Y is high when A is high and B is low, or Y is high when A is low, A is low, and C is high. Okay, the Boolean relationship between the output Y and the inputs A, B, C can be obtained in a few ways. Since we have these lingual descriptions of the output Y, the simplest way to express the mathematical logic expression for Y is based on this description, in which we can write right away Y equals to A B bar, because A is high and B is low, or A bar C. Okay, here we use this plus sign to represent the logic OR operator. So we need to be careful with not to get mixed up between the logic OR operator and the arithmetic addition operator, or plus, that we are going to learn in the arithmetic circuit chapter. Alright, the Boolean logic expression can also be derived from the truth table, as we know. In this case, we can construct a truth table with the columns A, B, C, and Y. And we list down all the possible binary combination between the inputs A, B, C. So obviously there are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 1, 1. Then we assign the value of Y based on this description. Y is high when A is high and B is low, or when A is low and C is high, in which the value of Y, let's use other color, is high when A is high and B is low, where this A high, B low, this cell and this cell should carry output 1, and A is low and C is high corresponds to this cell number 1 and number 3. So others should carry value zeros. Hence, based on this truth table, the mathematical logic expression of Y can be obtained either in terms of min-terms expression, such that Y equals to sigma small m bracket 1, 3, 4, 5, which equivalents to A bar, B bar, C, or A bar, B, C, or A, B bar, C bar, or A, B bar, C. This expression is known as the standard. The standard sum of product form. This standard algebraic expression is in fact related to the binary code of the combination between A, B, C. For example, this A bar, B bar, C terms corresponds to this value 1, that related to a combination of A, B, C that gives the code 0, 0, 1. So the first term on the right hand side is actually can be denoted as M1 followed by M3. So this can also represent M1, M3, or M4, or M5. Or in compact form, we wrote them as the summation notation, like the top. Again, please not to be confused with the term summation, because it corresponds to the logic OR operation, not the arithmetic addition operation. Okay. In some cases, a standard SOP expression can be simplified. For example, in this case, if we take this expression, if we notice, we can factorize the term A bar C from the first two terms, such that this becomes A bar C B bar or B. Or, and then we can factorize the term A B bar from the last two terms, such that it becomes A B bar C bar or C. As we know, the Boolean identity gives this kind of expression equals to 1. So we get this eventually equals to A bar C or A B bar. Alright, we can also derive the Boolean logic expression using the famous Karnaugh map, or we often call it K-map. Here we can simply build an 8 cells K-map that corresponds to the 3 input variables A, B, C, like this. Okay, Let us assign the variables a, b at the top of this map and c at the left side of this map, and we list the column index according to the gray code, such as 0, 0, 0, 1, 1, 1, 1, 0, and the value 0, 1 for the row index. And of course, this K-map is for output y. Okay, then we transfer the value of y from the truth table to this K-map. So we fill out these cells with 0, 1, 0, 1, 1, 1, 0, 0. And obviously, we can create two groups in which this gives the expression or the term a bar c, and another one gives the expression a b bar. And finally, based on this K-map, we can show that y equals to a bar c or a b bar. That provides the same answer with the previous way. Managed to derive the Boolean expression for the outputs, such that y equals to a bar c or a b bar. Then we come to the question how to realize the outputs by using the combinational logic devices. Since the output is expressed in the sum of product form, the straightforward solution to realize the output is by using the combination of AND gates and OR gates with some NOT gates, or we often call it as inverters. So here, using two AND gates and two inverters, one here, another one here, and do this connection A, C, then A, B, and feed these two lines to an OR gate. We managed to produce output Y. That's pretty easy, right? By the way, in practice, we often encounter systems with more outputs. Suppose that there is another output, such as Z equals to A bar B bar or ABC. Of course, Z can be realized using the similar way that we have done for Y, that is using two AND gates and one OR gate. But let's think of using a more systematic or more structured device to realize both outputs, Y and Z. If we rewrite both outputs in terms of the mean terms, such as Y equals to A bar B bar C or A bar B C or A B bar C bar or A B bar C, and Z equals to A bar B bar C bar or A bar B bar C or ABC. We can think of a device that produces all the minterms between the inputs A, B, C. Okay, let's think of this device. Let's place the inputs A, B, C at the left side of this device, and then draw the lines for ABC. And we place one inverter for each ABC like this. One for B, another one for C, and we extend the lines okay. Then since we have 8 minterms between A, B, C, we use 8 AND gates, and we arrange like this. 1 here, 2, 3, 4, 5, 6, 7, 8. So we wish the first AND gate to produce A bar, B bar, C bar, followed by A bar, B bar, C. So I often denotes each AND gate with the decimal number as the code. So this is number 0, number 1, number 2, 3, 4, 5, 6, 7. So number 2 corresponds to A bar, B, C bar. Number 3 corresponds to A bar, B, C. Number 4, A, B bar, C bar. Number 5, A, B bar, C. Number 6, A, B, C bar. And number 7, A, B, C. Okay, to get this kind of outputs for each of the AND gates, so we do these connections. So A bar is connected to this one, this AND gate, and this AND gate, and the following AND gates are connected to A. Okay, and we do this connection, B bar here, and then B, B, B bar, B bar, B, B, and C bar here, C, C bar, C, C bar, C, C bar, and C. All right. This arrangement is in fact form a device known as the decoder. So this is a decoder, or more specifically called the 3 to 8 line decoder. So the decoder is also called the minterms generator because it generates minterms. The decoder has a specific structure, that is, it consists of input line with inverter array here, or often known as the buffer inverter. And followed by the AND gate array. Here are the AND gate array, or we just call it as AND array. Okay, so the number of AND gate is in fact 2 power the number of inputs, which is 2 power 3. So now, how to make use of this decoder to realize both outputs Y and Z? It is not so difficult since we already have the expression of Y and Z in the form of minterms. So now, if we give these minterms numbers, so this is number 1, this is number 3, this is number 4, and number 5. So to produce y, let's extend this line a little bit. So to produce y, I must take the output from AND gates number 1, 3, 4, 5 to this OR gate. 1, 3, 4, 5. And to produce that, I require AND gate number 0, number 1, and number 7. Zero, number 1, and AND gate number 7. So using an OR gate for y and do this connection, and another OR gate for z with this connection, we managed to realize both of them. Alright, now we are getting into the real topic of this video lesson, which is the PLD, stand for Programmable Logic Device. The general structure of PLD is they consist of a set of buffer inverter connected from the input lines. So here, if I have an input A, so this line will give me A, of course. And if I place an inverter here, this line at the top produce A bar. So the direct connections to the inputs is known as buffer. So suppose that we have a number of buffer inverter connected to the defined inputs, and we have some more buffer inverter. Okay, this buffer inverter followed by the connection to a set of AND gates. So we are supposed to have a set of AND gates connected to the output of the buffer inverter. And so on. This followed by the set of OR gates, which is known as the OR array. As many number as possible. So these AND gates produce the product terms. So these product terms serve as the input to this set of OR gates, which is known as the OR array. So the number of input lines to the gates defined by the specification of the device. So again, I repeat. So this part is known as the buffer inverter. This part is called the AND gate array, or simply AND array. And the bottom part is called the OR array. All right. So in PLDs, one or both gate array, one or both AND array and OR array are programmable. So the word programmable refers to the connection within the gate array that can be specified by the user or by the programmer. There are three types of PLDs that will be mentioned here. The first is known as the programmable read-only memory, or in short PROM. The second is the programmable logic array, or PLA. And the third is the programmable array logic, or in short PAL. So these types of PLDs are defined based on which gate array is programmable in the device. So based on this table, for PROM, the AND array is fixed, whereas the OR array is programmable. For PLA, both AND array and OR array are programmable. And for PAL, it is the opposite of the PROM, which is its AND array is programmable and its OR array is fixed. Okay, we might be wondering how a device can be programmable or how the connection can be modified in real application. This can be done by fabricating a gate with fuses. Let me erase this first. Okay, suppose that we have this set of inputs, A bar, B bar, C bar. If we directly connect all these inputs to the AND gate, we will get the output A bar, B bar, C bar, which is in fact equals to 0, because based on the Boolean identity, one variable and with its complements, one variable and with its complements equals to 0. So this basically are 0. By the way, how to make this AND gate programmable? So this can be done by fabricating a gate with fuses. As an example, if we add fuses before the gate, initially, of course, we will get this output A bar, B bar, C bar, which equals to 0. Suppose that I wish to have the output produced by this AND gate, which is A, B bar, C bar. So this can be achieved by doing a programming and then define that the connection of the A bar, B, and C are unwanted. So in hardware, in the real hardware, this connection will be removed by blowing the corresponding fuses. So in this case, this fuse, this, and this will be blown to produce A, B bar, C bar. So that is one way how the connection of a device can be modified or programmable. Now let's go back to the PLD and get familiar with its notation. Okay, to avoid too many wire lines, we will use the simplified notation. So suppose that this is a PROM with certain number of gates. Now take a look at the buffer inverter connection. We simply drawing this buffer inverter by placing a triangle symbol and then place a bubble beside the triangle. So the lines that comes out from the buffer, from the triangle, is the true value of A, which is A, and the lines that comes out from the bubble is the complement value for A, which is A bar. So similarly, we draw the same symbol for the remaining inputs. So this how we do the simplification notation for the buffer inverter. All right, let's turn our focus to the AND array. To simplify the notation, instead of drawing all these lines, or as many lines as the input to these AND gates, we just represent them with a single line. All right. Then we indicate which line is connected to the AND gate by placing the dots or cross at the intersection of the lines. For example, if we do this kind of connection, let's say this is C. So this AND gate produces A bar, B bar, C bar. And similarly, if I do this kind of connection, so the second AND gate produces A bar, B bar, C. Similarly, we can also use the same notation in the OR array, in which we just draw a single line to represent as many lines as in the OR array. So since if this is a PROM, the connection in the AND array is fixed, and the connection in the OR array is programmable. So we use now I think let's realize the output Y and Z. So we require 8 AND gates. One, two, three, four, five, 6, 7, 8, and then let's complete all the connections in the AND array. Okay, so to produce Y, and Z. So since Y equals to this, okay, so we complete these lines. So Y equals to A B bar C, A bar B bar C, A bar B C, A B bar C bar, and A B bar C. So while Z is A bar B bar C bar, so this should be Y, and that Z, A bar, B bar, C bar, A bar, B bar, C, and ABC. Okay, notice that again, we assume realizing Y and Z using the PROM, so we use dot symbol in the AND array to indicate fixed connection and cross symbol in the OR array to indicate programmable connection.